Welcome folks, we are now interested in learning how to simulate the natural response of source-free RL circuits using PSPICE Orcad. So let us assume that we have a circuit like this one where we have a switching circuit. We have some form of a DC source into an RL circuit. Basically the circuit has a bunch of resistors and one inductor. Now you need to pay attention to the switch here. Basically by paying attention to the switch here, you know that this switch gonna be the switch will transition from applying a 5 volts to short circuit at t equals 0. So to understand that this circuit becomes source free through the transition of the switch, I recommend you to draw the circuit for t before the switching and t after the switching. So for t less than 0 before the switching, the switch was connected to the voltage source, so that's what we have here. So we have a 5 volts is connected to the RLC circuit, and this happening for a very long time. That means that this is a DC circuit, and we know that at DC the inductor is a short circuit, so I'm gonna model the inductor with short circuit like this. And then after switching for t greater than 0, the switch becomes shorted, and when the switch becomes shorted, this 5 volts voltage source is not applied to the circuit anymore. So the circuit will look like this. We basically remove the 5 volts from the circuit. So after switching, we're gonna draw back the inductor again. So the idea is that before switching, we can calculate the current through the inductor IL, and by calculating the current through the inductor IL, this current at switching time has to be the same. So right before switching and right after switching, the inductor current gonna be the same. And the reason is the derivative of the current got to be continuous. If the current is not continuous and it doesn't have a derivative, a finite derivative, the voltage across the inductor gonna be infinite, and that's gonna basically burn the whole circuit. So it doesn't work. We have to force the current before switching and right after switching to be the same current through the inductor. It's a continuous current. Anyway, so what happened is after switching, the current through the inductor will continue to flow. This stored energy will slowly dissipate into the resistors. So the RL circuit will continue to have current flowing through the circuit. So it will take some time for that stored energy into the coil to be dissipated. The beauty of the circuit that once you remove the source, you're gonna have one equivalent resistance across the inductor, and this circuit after switching is governed by a first order differential equation. Now the solution to the current through the inductor is basically before switching, the current through the inductor gonna be constant. It's basically the initial condition. It's the same current flowing in at t equals 0, just right before switching. After switching, the current through the inductor gonna exponentially decay as a function of time. It's basically gonna be IL at 0 times e to the minus t over tau, where tau is the time constant of the RL circuit, and tau is defined as L over R equivalent. In this particular circuit, R equivalent is 435 ohms. Now keep in mind that R equivalent needed to be measured after switching. So after switching, draw the circuit after switching, you're going to see that those two resistors are in parallel, which are in series with this resistor. So here we're going to have 235 ohms, the equivalent of two parallel resistors, plus 200. That's basically, this is equal to, this basically equals to 435 ohms. So if you gonna plot this function IL of t, it's gonna be basically some constant value until t equals 0. When the switch opens, the voltage source becomes short, basically gonna exponentially decay as a function of time. Now if you calculate tau second later, so when t equals tau, you're gonna have I naught times e to the -1. When t equals tau, the current will drop 63.2% of the total range. We call it the peak-to-peak value. So if the current drops 63.2% of the peak-to-peak value, then tau second has elapsed. Tau second elapses when 63.2% of the peak-to-peak value have dropped. In this particular circuit, tau is calculated to be 4.25 microseconds. So let's simulate the circuit in Orcad. Now the thing about simulating the switch with Orcad is that we're gonna use a rectangular pulse. A rectangular pulse voltage source will be used to simulate the switch, as long as the pulse width of the rectangular pulse is 5 times bigger than tau. Since tau is 4.25 microseconds, we can use a rectangular pulse to be 5 times bigger than that. In my simulation, I will use about 10 times bigger than that, so I would say that the pulse width is going to be around 50 micro, and that will guarantee that the time that the current will reach 0 as t approaches infinity. So let's go to PSPICE Orcad and simulate this circuit. So once we load Orcad, I'm gonna come to File. I will start a new project. I will give this particular circuit a name called source free, source underscore free, and I will do RL underscore circuit 1. Make sure it's a PSPICE analog or mixed AD. We're gonna create a blank project, and now I'm going to build the circuit. So the first thing I'm gonna do is I'm gonna use V pulse. It's a voltage source that's basically will generate rectangular pulse, which will mimic the on-off switch for the voltage source. I'm gonna click on it here. I'm gonna place it. Let me zoom in a little bit to see what those components are inside. We're gonna basically enter some parameters for that. So in the circuit, the voltage source initially started to be 5 volts. So I'm gonna say that's 5 volts. Then for V1, then V2 gonna be basically the second value of the voltage. It's gonna drop to 0. The switch was initially connected to the 5 volts, so it reads 5 volts, and then at t equals 0, it moves to the 0 volt. Basically, it becomes a short circuit. Now TD stands for time delay. Basically, it says that when the pulse will start to be triggering. So I'm gonna say that this pulse is gonna start at 0 seconds, so there is no time delay for it. Orcad is a numerical method, so we can't say that it will jump from 5 to 0, jump down from 5 to 0 volts in 0 seconds. There has to be some time for it to do that. So that's where we have the TR and the TF. The TR stands for the time rise, and the TF stands for the time fall. So I'm gonna give each one of those to be 1 nanoseconds, because we simulate the circuits using numerical methods, and that means we have to define derivatives. When we define derivatives, we can't jump the voltage from 0 to 5 volts in 0 seconds. We have to have a finite time rise and time fall. The PW stands for the pulse width. Now the pulse width got to be bigger than 5 tau. So, and we know that tau for the circuit we are trying to build is 5.25 microsecond. So I will say that if I do it 10 times that, that's going to be 42, but to make it rounded, I will make it 50 microsecond. That's the pulse width. And then I will make the duty cycle to be 50%. That means the pulse will be 50% on, 50% off. That means the period, the entire period, will be twice times the pulse width, which is 100 micro. So basically what we created here is a rectangular pulse that the frequency of this rectangular pulse will be 1 over the time period, which is 10 kilohertz. So we are applying 10 kilohertz rectangular pulse to the circuit, and then it's going to be 50% on, 50% off, 50 microsecond on, 50 microseconds off. The switching will start from 5, will drop to 0, 0 delay, and the time rise and time fall for the pulse is going to be 1 nanosecond each. This is the voltage source that we are applying to the circuit, which mimics the switching of adding and removing the 5 volts from the circuit. Then we're going to add the resistors. So I'm going to come to the parts. I will write R stands for resistor, part of the analog library. I'm going to add a resistor here. This resistor going to read 470 ohms. So I'm going to write here 470, and then I'm going to add another resistor. I will click on R to rotate it. And then once I rotate this R, I will make it also 470 ohms. And then I will have the inductor going to be L under the analog library. So here is the inductor we will use, and the inductor will have the value of 1 millihenry. So I will make that to be 1 millihenry. And finally we have one more resistor R, that is R3, part of the analog library. I will click on R to rotate it, and then this resistor going to be 200 ohm. 200 ohm. The value of this resistor is 200 ohms, and then I'm going to add a ground. You always need to have a ground for PSPICE circuits. Now we are going to connect the rest of the circuit. So that's what we have here. And then, in fact, let me lower that a little bit. And then go back here, connect this to that, and this is the ground. And now we are going to define a new simulation. I'm going to call it Sim1 for this project, and we're going to do a transient analysis. Now when you do transient analysis, you need to be careful. So here I have 100 microsecond for complete period, so I might want it to show like 5 periods, so I will do 500 micro, and then the maximum step size I would do like 10 nano. I'll do apply. Okay, so basically you need to define what's the simulation runtime or stop time, and what's the maximum step size, basically how fine your resolution gonna be. And I'm going to measure the current through the inductor coming in. So let's see what's the current going through the inductor of this circuit. Basically that's all what I need at this point. So let's run the simulation, and it's going to take some time, as you can see here. If I zoom in here a little bit, you can see that the current through the inductor will exponentially decay as a function of time. If I go back and zoom out, let's do the whole thing, you can see that initially the current through the inductor before switching was around 5.7, more or less 7.5 milliamp. So that's how much current we have through the inductor. And then once we remove the switch, the current through the inductor will start exponentially dropping. So, and this will happen every time we go through the pulse, every time we turn off the pulse. So this is a very good way to mimic the source-free circuit. Basically you want to look at the response of the circuit after removing the voltage source. And this basically gonna be in this area over here. Right, so you can see that you have a constant current until we turn off the switch, and that's current through the inductor will exponentially decay as shown here. If we go back to the circuit, we know that the current through the inductor is the same current going through the resistor. So instead of measuring the current through the inductor, I can measure the voltage across R3. Because in the laboratory, when we use oscilloscopes to measure those pulses, it is a little bit hard for us to measure the current through the inductor. It is easier for us to measure the voltage using the oscilloscope. So in the lab, when we wanted to test such a circuit, we can measure the voltage across the 200 ohm resistor. And this basically will indicate what's the current through the inductor gonna be. So now I can basically rerun the simulation with that. So now this is what I have, is basically the voltage will go up to 1.18 volts, and then it will exponentially decay as a function of time. To even make my simulation better now, I can compare it to the voltage of the input. And now what I have is that you can see when the voltage will jump down from 5 volts to 0 volts, this is the input voltage in red, then you can see that the output voltage in green will basically exponentially decay as a function of time. So, and then from here we can calculate tau, which is the time required for the output voltage to drop 63.2% of the peak-to-peak value. So to calculate the time required to drop will basically be your tau. Anyway, you were able to simulate the circuit using PSPICE Orcad. So now we are interested in showing you how to use PSPICE Orcad to simulate the natural response of source-free RC circuits. How would we simulate source-free RC circuits? So basically, if we have a circuit like this one, and here again we have a switch, and this switch basically gonna add 5 volts to an RC circuit for t less than 0, and at t greater than 0 the switch becomes shorted. That means we're gonna remove the 5 volts out, and we're gonna have a source-free RC circuit. So I recommend you to draw the circuit for t less than 0, and for t less than 0 we're gonna have the 5 volts connected to the RC circuit. Then this behaves as a DC circuit because this voltage source is not changing for t less than 0, and you're gonna have the resistors R1, R2, R3, but the capacitor becomes open circuit because this circuit is DC. So before switching, the capacitor is basically a DC, is basically an open circuit. For t greater than 0, the switch becomes short, so we're gonna remove the 5 volts. That's what we have here when we draw the circuit. You're gonna have R1, R2, R3, and then we're gonna bring the capacitor back to the circuit. Now, this particular circuit have observed or have seen a switching at t equals 0, but you will end up with a first order differential equation. This capacitor has electrostatic voltage or electric field stored inside the capacitor. This electric field or voltage is basically stored energy, which is proportional to the charges across that capacitor. Now, this stored energy that is initially stored at t equals 0, when the switch basically becomes short circuit, will force the stored energy to be dissipated through those resistors. So whatever stored energy we have here gonna be dissipated through the equivalent resistance across the capacitor. That means that the charges will move back into the circuit, and the voltage across the capacitor will exponentially decay. The solution to the first order differential equation of the RC circuit, when we remove the source from it, becomes source-free RC circuit, which means that's the natural response of the circuit is basically the initial condition. The initial voltage across the capacitor is the one that will take over. So we can say that VC of t going to be constant before switching. It's going to be VC at 0 for t less than 0, but VC going to be exponentially decaying function for t greater than 0, where it will be VC at 0, that's the initial condition, times e to the minus t over tau. And tau is basically equal to R equivalent times C. So if you wanted to find R equivalent here, it's going to be the 1K in parallel with the 2.2K, and that will be in series with the 4.7K. So when we plot the response of the voltage across the capacitor, it's going to basically be some constant value, and then it will exponentially decay as a function of time. And the time required for the voltage to drop 63.2% of the peak-to-peak value is what we call tau. So the time constant is the time required to drop 63.2% of the peak-to-peak value, because when we plug in t equals tau here, we have e to the negative 1, and e to the negative 1 gonna give us 0.632 of the peak-to-peak value. So R equivalent for the circuit was found to be 5.39 kilo ohms, and tau is found to be 53.87 microsecond. So to simulate the circuit, I would basically need to use the pulse width of the rectangular pulse to be around the 5 times tau. So I would say that it needs to be bigger than 530 microseconds. The pulse width needs to be greater than 5 tau, and that should be greater than 0.27 millisecond. So in my simulation, when I build Orcad, I will use the pulse width to be a half millisecond. So let's go ahead and move on to show you how we can simulate the circuit using PSPICE Orcad. So here I have loaded the PSPICE Orcad. I'm gonna come to File. I will click on New Project. I will say that it's source-free. RC1 is basically the file name. I'll call it source-free RC1. I'll select PSPICE Analog. We'll create blank project. So here is my blank project. I will start with applying the V-pulse. So I will write V-pulse, which is part of the source library. I'll click on this. I will zoom in to enter the values for the V-pulse. So V-pulse initially starts at 5 volts. Then it will drop to 0 volts. We will start at 0. The time rise is gonna be 1 nano. The time fall gonna be 1 nano. You need to make sure that the time rise and the time fall are very, very small, which represents a rectangular pulse. So here I'm gonna choose the pulse width to be 0.5 millisecond, and the period to be 1 millisecond, which is twice that. So basically I'm applying a 1 kilohertz signal to the system. And then we're gonna build the circuit. So we're gonna start with the resistors R. So the first resistor gonna be 1K, and then the second resistor gonna be 2.2K, and then the third resistor going to be 4.7K. So this resistor here gonna be 2.2K, and this resistor over here it's gonna be 4.7K. And then finally we're gonna have a capacitor which has the symbol C. We're gonna have a capacitor, we'll click on R to rotate. We're gonna have a capacitor here to be 10 nano. And now we're gonna need one ground. And we are ready to connect the circuit. So we're gonna connect this voltage source to this resistor, R1 to R3 and to R2, and then R3 to the cap, and then the cap gonna go to the resistor, to ground, and to the voltage source. So this is basically the circuit that we're trying to simulate. Let me just zoom one notch out. I'm gonna basically create a simulation. I'm gonna call it Sim1. Now I'm gonna show you different ways to do it. So I know that the pulse width gonna be half a millisecond. So I will run the first pulse 0.5 millisecond, and I will say that the maximum step size is gonna be 10 nano. So basically here, all what I'm gonna plot is the first half of the rectangular pulse, which basically represents removing the source from the circuit. So that's another trick to use to simulate source-free circuit, is build a rectangular pulse with very wide pulse width and only simulate it over the first half period, so you don't have to see the entire rectangular pulse. We're gonna say apply, okay. Now I'm gonna add the voltage prop across the capacitor. Let me also add VI. Yeah, we made a mistake. This is gonna be 2.2K. Let's resimulate the circuit again. So that's what we have, is basically the voltage dropped from 5 to 0 at 0 second, and the green line is the voltage across the capacitor as a function of time. It is an exponential decaying function, and that's basically the voltage across the capacitor. We don't have to measure the voltages, so we can remove that and this. Now we're going to measure the current through the capacitor. Now keep in mind that the current through the capacitor is going to be negative because the current will leave the capacitor. So the current will leave the capacitor when the source is 0 to discharge the capacitor through those two resistors. So let's see what we have now when we measure the current. So you can see that the current through the capacitor was 0 initially, then it dropped to negative 600. And you can see that the current through the capacitor is not continuous. The voltage is, but the current is not. So it dropped to negative 600 micro, and then it started to basically increase exponentially until it fully discharges through the load. We can come back to re-edit the simulation, and instead of having one pulse, one half pulse, we can basically run the simulation for 2 milliseconds. And let's say okay here. So I'm gonna basically measure the voltage across the capacitor, and let's see what happens to the voltage across the capacitor. And I'm gonna measure the voltage of V out versus VI. So that is what we have. Initially the voltage will drop from 5 to 0, and the voltage across the capacitor will drop to 0. Then when we apply the 5 volts again, the voltage across the capacitor will exponentially increase. The natural response is basically the response when we remove the voltage source. So this portion here is the natural response of the circuit, which is the same as this portion over here. So in the lab, you're gonna apply a rectangular pulse like this, but you want to zoom on the scope until you get this portion of the voltage across the capacitor. This basically says that it's the natural response of the voltage across the capacitor. Initially carries the initial condition until we remove the voltage source. We'll move from 5 to 0. Then the voltage across the capacitor will exponentially decay until it hits 0 around 5 times the time constant. So we can say that around here we can assume that the voltage across the capacitor is 0. I hope you like this video, and now you know how to simulate RL and RC circuits using PSPICE Orcad. Thank you and good luck to you.